We're going to consider now a question about linear independence, and that is, how can you tell if a given list of functions is linearly independent or linearly dependent? Let me remind you now, this question does make sense. We don't normally think of functions as being vectors, and normally it's vectors to which we apply the ideas of linear independence and linear dependence. But remember, functions can be thought of as vectors in a vector space, this vector space of all functions. So that being noted, given a list of functions, how do you decide this? Independent or dependent? Well, we've done an example previously, and we did specifically an example involving polynomials. And that was kind of a cheap trick because we got lucky there. We broke it down to coefficients. Right? You write down what it would mean for a list of polynomials to be independent or dependent, and realize that you can then write simply down a system of equations about the coefficients in those polynomials. And that's just a lucky break about the structure of polynomials. Okay, so in general, though, if the functions aren't polynomials, that doesn't work. There are no coefficients to center your argument around. So it just doesn't work. So we have a non-trivial question here as to how do you decide, given a list of functions, is that list of functions independent or dependent? Well, we're going to make an argument here. So we have a list of functions. We do need for these functions to be at least that differentiable for this argument to work. So our result is going to be correspondingly limited. It's still very nice. And what we're going to do is look at possible solutions to this system. Right. Okay, now importantly, so we're looking at a linear combination of functions. These functions are vectors in a vector space, in that vector space. And so this 0 here is the 0 function. It is a linear combination of functions. So it itself is a function. So I'm not interested in cases where this might be 0 for some value of x. I'm interested in cases where this is 0 for all x. Okay. All right. We're going to come at this indirectly. We're going to start off with a question that's not really direct, does not seem to be a fair starting question, and that is we're going to start off by assuming that we have a list of functions that's dependent. Well, gosh, shouldn't really assume that. I'm trying to decide that. Well, what we're going to do is make an argument that's backwards. We're going to start by assuming it, we're going to get a conclusion, and that conclusion will allow us to argue backwards. So here we go. Suppose we have a dependent list of functions. Well, that's what that means. A dependent list of functions, there is a linear combination of them that adds up to the 0 function. And furthermore, it's not just a linear combination, it's a non-trivial. It's a significant linear combination that adds up to the 0 function. Okay. Now take a derivative of that equation. And then take a derivative of that equation, etc., etc. And keep going until you've gone down to the n-1th derivative. Now this is all perfectly legal algebra. It's not clear why this is useful, but it is legal. Now the reason we stop at n-1 is because at this point you'll notice that there are n terms in each of these equations, and I have n equations. Grand total of n equations, because I started with what you might call the 0th derivative. So stopping at the n-1 derivative, grand total, that gives me n. And you can view this as kind of a system of equations. It's sort of a system of equations where the variables are C1 through Cn. That's a point of view that you could take on this algebra here. And that's how we're going to rewrite it. This is the exact same thing, written as a matrix equation. And take a moment to persuade yourself that this matrix algebra here is equivalent to this algebra here. Okay. Right, so now don't forget our idea here, being as these functions are dependent. This can be done with a significant list of coefficients C. And therefore, this can be accomplished with a significant list of C's. In other words, these coefficients not all zero. In other words, we have a non-trivial solution to this system of equations. And this is a square matrix. We have a square matrix, homogeneous system with non-trivial solutions. And that means that this square matrix is singular, which means a long list of things, but among them it means that this matrix has a determinant that's equal to 0. So this great big determinant of this great big matrix made up of a bunch of functions, that determinant must be 0. All right, this determinant is called the Wronskian of that list of functions. Take your functions, write them down as the top row of your matrix, start taking derivatives, keep going until you get a square matrix, take the determinant. That's called the Wronskian. Okay, all right, now, not clear yet why we would care about this construction called the Wronskian. Keep in mind, we got to the Wronskian by considering an assumption that we really shouldn't be assuming. We're assuming something that in reality we're trying to decide. Okay, but let's write down, let's summarize what we've said anyway. If this list of functions is dependent, we've shown that this Wronskian must equal to 0. And here we write that down. If the list is dependent, the Wronskian is equal to 0. Mind you, that's equal to 0 for all values of x. Every value of x. Right? Because this algebra up here is true for every value of x. Okay. All right. So we have an implication. And the nice thing about implications is you can also then write down the contrapositive. So this implies this. Another way to say that is that if this is not true, if it fails to be the case that the Wronskian is always 0, said differently, if the Wronskian is ever, for any value of x, if the Wronskian is ever non-zero, then I know that couldn't possibly be true, and therefore the list of functions is linearly independent. So even though we started off seemingly by making an unfair assumption about something we were trying to decide, what we've turned that around into is a test, an easily checked algebraic test, the conclusion of which is possible clarity on the question we're interested in, namely, is this list of functions independent or dependent? Okay, so let's see a quick example. This is the big theorem about Wronskians. Make sure you memorize this theorem. So here's an example. There's a list of functions, and I would like to know if that list of functions is independent. Okay, so we're going to compute our Wronskian. Note, this theorem says you've got to compute the Wronskian, find some value of x where the Wronskian is non-zero, and then you get to draw your conclusion. Okay, so let's do that. We construct our Wronskian by taking our list of functions. We make those the top row. We start taking derivatives. Keep taking derivatives till you get a square matrix. The Wronskian is the determinant of that great big square matrix. And a little bit of algebra to do here, and there it is. There's your Wronskian. It's 2x cubed. Now keep in mind, our goal was to find anywhere, any value of x, that the Wronskian is non-zero. Now, is that the case here? Are there any values of x for which this is not 0? Well, of course. This is non-zero usually. Right, now it happens to be 0 sometimes. That's not our concern. Right? The concern is it ever non-zero? This function is not only at least once non-zero, it is usually non-zero. And therefore the list of functions is independent, and we've answered this question conclusively.